All right, welcome back. So in this lecture, we're going to talk about polarity because it's something that I didn't really talk about much in previous lectures, and I wanted to make sure that everyone understood the concept. All right, so let's say polarity of molecules. And of course, in previous lectures, I mentioned how some bonds are, some bonds are polar. And that is their electrons are shared unequally. So an example of this would be water. So I'll draw my lone pairs. And remember, water is tetrahedral. So if these hydrogens are in the plane of the board here, then one lone pair is sticking out and one sticking back. Now I made some models here to help visualize this. So here's the water, and one lone pair would be sticking that way and one that way. So water illustrates that we need, illustrates the two things that we need. Okay, for one, we need these polar bonds, polar covalent bonds. And maybe I'll draw it in green here. So usually we draw a little arrow and kind of have a little cross there to make a plus. This means the electrons are pulled more towards the oxygen, pulled more towards the more electronegative atom. And you could look up on the Pauling electronegativity scale, oxygen's 3.5, hydrogen's 2.1. As long as your difference, I think, is greater than maybe 1, it's a fairly polar bond. Maybe it was greater than 0.7. I don't remember. Anyway, that's not what's important. What's important is we do have a significant electronegativity difference, and so we've got electron density pulled towards the oxygen, which gives us, and I'll use a lowercase Greek letter delta, a delta minus on the oxygen end and a delta plus on the hydrogen ends. And that gives us a net dipole. Okay, so there's an electrical dipole here. We've got a partial negative charge on this the red end of the molecule, the water end, partial positive over here. So this will, the partial negative will be attracted to other positive charges, and the partial positive will be attracted to other negative charges. And that's actually how how water, why it has the properties that it does, because it is polar, and can also engage in what we call hydrogen bonding, which I'll talk more about in chapter 10. So these guys would tend to want to sort of be attracted like that, or maybe something like, kind of like that. Now, one thing that the water shows, and I didn't state here, is that not only do we need polar bonds, so bonds must be polar, and then we need correct geometry. And that is, if our polar bonds are offsetting, then our molecule is not polar. So we'll say here, offsetting polar bonds equals non-polar molecule. Okay, and so an example of that, could be something like, let's do this. Let's take these guys off. We'll look at some examples here. So we could have, let's say, carbon tetrachloride. Now the carbon-chlorine bond is polar, so the electron density is going to be pulled towards these chlorines. Well, that net pulling is going to offset. It's going to be equal and opposite. And the result is that it cancels out. So let's take a look at some examples of those. I want you guys pause and write this down if you want. Okay? So if I have carbon, chlorine, chlorine, I'm not going to draw all the lone pairs in here. Cl, Cl. So my bonds here are polar, but the net result is negative charge is more on the outside, positive more on the inside. That's not a dipole. So this one here is nonpolar. Now, if I replace one chlorine with a hydrogen, well, now I have a net pulling of electrons towards this end of the molecule. These three, I'm holding here, these three chlorines, and away from this hydrogen. So I can go ahead and draw this. So this is chloromethane. So let's just put the hydrogen up here. Why not? Cl, Cl, Cl. That's an L. Sorry. And I've got a net pulling of electrons towards the chlorines. A little bit from the hydrogen towards the carbon. Carbon is slightly more electronegative than hydrogen, but it's pretty close. Most carbon-hydrogen bonds we consider to be nonpolar. So we have a net pulling towards this side. So we've got a net delta minus here and delta plus up there. And this guy is polar. And just to show the model again, it looks like this. And so we have a net pulling of electrons that way, this way, that way. So there's a net pulling towards this bottom part and away from this top part. Now, let's take a look at if we had a molecule like this. So this is dichloromethane, also called methylene chloride. And it's important to draw it as a tetrahedron. Now, I'm going to go back here and make these script L's, just so you know that that's a chlorine there, and just so you don't think it's a carbon. And it's important to draw this like a tetrahedron because this shows how electron density is pulled towards this chlorine and this chlorine. So there's more electron density on this side of the molecule than there is on this side. And we can write that as follows. So delta minus here, delta plus there. Now contrast that to if we had something that was square planar. So this guy's polar. So let's say we had something like that was square. Well, I'll just show it. I won't write it on the board here. Something that was square planar like this. Well, now these chlorines are pulling electron density equally away from the middle, so there's no net dipole. And if you aren't drawing things like a tetrahedron, you may end up drawing your Lewis structure so it looks like this. Looking at it face on there, or head on, which kind of looks like a cross, which shows the importance of drawing things using this wedge and dash formula. All right. Lastly, let's look at chloroform. I'll put my chlorine here, the hydrogen there, and now we've got, again, whoops, that's the wrong one. That's not a chlorine, that's a hydrogen. Come on, Wayne. we have electron density being pulled towards the chlorine, so we have a partial negative there, partial positive on the other end. And this is also polar. And model-wise, let's see what it looks like. So it would look like this. So we've got electron density pulled towards this chlorine and away from this side. So there's a net pulling that way. So we get a net dipole, and chloroform is polar. It's not as polar as, let's say, water or other molecules. So you can have other molecules that are also common polar molecules. Ammonia has a delta minus there, delta plus on the other end. It's a delta, not a, I don't know what that looked like. And let's see, something like this, trigonoplanar, if everything was symmetric, that would be non-polar. But if I had, say, a hydrogen instead of fluorines, or chlorines rather, now it would be polar. There'd be net negative charge on this side, net positive up here. Another one I wanted to show you was formaldehyde. And here we've got our net pulling of electron density from the carbon to the oxygen. So we've got a delta minus there and a delta plus where the carbon is. So even though it's a double bond, it's still very polar. In fact, the carbon-oxygen double bond, I believe, is more polar than the carbon-oxygen single bond. So this molecule is polar, and the red end up here where the oxygen is partially negative, partial positive charge on the carbon. And you can contrast this to carbon dioxide. Let me just write it here, polar and polar. And CO2 is nonpolar because so it's linear. I'm not going to make the model. It's linear, and we've got partial negative on either end and partial positive in the middle. Well, that's not a dipole. It's not that one end is partially negative and one end is partially positive. So carbon dioxide is nonpolar. So again, there's two things to look for. One is you have to have polar covalent bonds, and you have to have the right geometry so that you have a net pulling of electron density towards one side of the molecule. And that is polarity. So that pretty much wraps up chapter 9, I believe. And till the next lecture, we'll see you at the White House. See you at the gray house with the white trim. I gotta get my catchphrase right. Oh well. See you guys later.